Ça marche? Okay, morning everyone. I'm going to be giving you guys a talk about rendering video, detailed look at video playback on Android. Hope you guys had a good day one, and thanks for coming here so early. So my name is Pierre-Antoine LaFayette. I am a software engineer at Facebook, and I work on, currently I work on VR stuff, so virtual reality rendering. I'm a graphics engineer / Android engineer. I'm currently working on a product called Oculus Quest, which is launching very soon. And I've been doing stuff in the 360 video space as well as in the 3D GLTF post space. So I gave a talk last year about rendering with the GLTF, which is a 3D graphics format. And now I'm going to talk to you guys today about a typical Android use case of playing back video. So this is a very, very important use case for Facebook. As you can imagine, as videos become more popular and more prevalent, we have now these auto-playing video feeds where whether you're on Instagram or on Facebook, you're going to be scrolling through them, you're going to have videos that start to play, and you're fetching data from the network, and you need to render that in an efficient way. And because you're scrolling as well, as you guys all know, when you're performing a scrolling animation or any kind of animation, you need to make sure you do that at 60 FPS and then you're not dropping frames. So it turns out that the video playback is one of the biggest contributors to frame drops in newsfeed for Facebook, and I'm going to get into the details of why that is. So we're going to kind of look at what's going on behind the scenes, something that some Android engineers, especially beginner Android engineers, don't end up doing. But this is something we kind of have to do at Facebook because we've done the research and we know that frame drops actually equates to lower engagement. So people are going to use your apps less if it's not performing well. So it's very important to optimize for this case. So to start, I'm going to take this back to kind of at the beginning of video playback on Android. So if you guys remember the earliest devices that we had on, Cupcake, Donut, Froyo, we had these very small screens. Because of that, it was acceptable to have, full screen video support only, essentially. And most of the time when you'd play back video, you would just, use the entire screen because it wouldn't really make sense to, just use part of the screen because it's so small. And there was no real robust inline video playback solution. I'm going to talk about what I mean by that. So in API 1, there was already this thing called VideoView, if some of you remember that. It extended SurfaceView, which I'm going to talk about. And it used MediaPlayer directly to load video by URI. So this was like the easiest way to actually embed video inside your Android application. And of course, it had the typical kind of playback controls that you expect from MediaPlayer. So what is SurfaceView? If you guys watched Romain and Chet's talk last year about how Android renders, they got into a bit of how SurfaceView works and how these different things are working under the hood. And I'm going to go a little bit further than they did. So at the most basic thing, the SurfaceView controls this video surface, essentially. And what ends up happening is you have a separate app window, and then you have a video window. And they're both going to be composited together on the screen by Surface Flinger, which is the System Compositor. And the way that it works is that the app window will basically cut out this transparent hole, and it'll basically composite the video underneath it. So the video is going to be behind, and then the app window is going to be in front. This is important for depth sorting. And of course, if the app window wants to composite UI like media controls, it could actually provide the UI and it'll be blended on top of the video. So the problem with this was that before NuGet, when there was some architectural change in the rendering code, the SurfaceView was not synchronized with the app window. So what that meant, if you tried to create a video feed like what I showed you with Instagram and Facebook, where you're scrolling through, the app window would animate and it would scroll up, but the SurfaceView would not actually track because it's asynchronous from the actual app window. So what you'd get is this kind of janky, kind of lagging experience, which was not really usable. So some people just chose to not include video in an inline feed. And another use case, not this specifically, but another part of this was in the Android browser. So prior to Honeycomb, there was no inline playback for the browser. I don't know if any of you guys remember that. I actually worked on this because I was at Qualcomm at the time working on the Android browser. So if you had a video tag, like an HTML5 video tag, in your web page, when you would hit play, what it would do is it would always load into full screen. Now this became a problem when you started having tablets before Honeycomb. So we started to have like these 6 or 7 inch tablets. So what it would mean is that anytime you have a video tag, it would always go to full screen, which could be a jarring experience. So it is a similar problem to this one, but just kind of at the browser level. But in the end, the rendering code is very similar, and I'll talk about how that stuff works. So this thing called Surface, what is it? It's essentially just a buffer that's managed by the compositor. So this is going to be something that's going to be handled directly by Surface Flinger. It's going to be pixels that are going to go out to the display, and I'll talk more about what that actually means. It can be backed by SurfaceTexture, which you guys are probably familiar with, if you've worked with TextureView, and I'll also go into more details about that later. And the key thing here is that when you use a surface view, you can actually use the surface in the native video buffer kind of format. So the video decoder and the videos in general will not be in the same format as what we want to use when we do like OpenGLES compositing, which is the graphics API that most Android stuff does. What ends up happening is you have to do the conversion. So if you're in like a YUV format or some other kind of native video format that the decoder works with, you have to convert that, which is an additional cost. So it costs you in bandwidth, it costs you in memory, and it costs you in power consumption. So this might not be something that you see, but anytime you're not using the native video format, there's an additional cost to it. And when you're blending things on top of it, there's also additional costs. So when you like want to do media controls. So if you were doing like full screen video, the most efficient way to do it would be to use a surface view and basically just use that direct video surface, which is going to be composited onto the screen. So that's the most efficient pipeline for video playback. So you guys probably all know about TextureView. It's quite popular now. It was introduced in the Honeycomb timeframe, and this was back when we used to be doing more CPU rendering because we could do it on these smaller screens. But once you started the pixel fill costs, once you started to get enough pixels on the screen with these tablets, it wasn't efficient enough. So we had to move to more GPU compositing and GPU rendering of certain things. So TextureView was introduced to allow 3D rendering. So you could render with a 3D API like OpenGLES, and you can also do playback of video onto this thing called a SurfaceTexture. So that's what it's backed by. And this would be composited into the window. So when you would render, or when you would render 3D content or your video or decode video into SurfaceTexture, which is shown on a texture view, it would actually be rendered directly into the app window. So instead of having like the app window with that cutout, you would actually have the full thing within video. So what that actually meant is that it would always be synchronized. So now that you have TextureView, you can actually implement the scrolling video feed because of the fact that it will be synchronized. But then again, after NuGet, SurfaceView became synchronized, so that became the most efficient way to do rendering. And I'll go more into details about that. So what is this SurfaceTexture thing? So a SurfaceTexture is basically it's a way to capture an image stream as an EGL external texture. EGL being the embedded graphics library, it's kind of an API that is used for interoperability between different graphics APIs like Vulkan, you might have heard of, OpenGLES, and it basically is. That's not what I wanted to say, but okay. So you've heard of this thing called a buffer queue, which basically is a way to synchronize access of these underlying buffers by a producer and a consumer. So this is very important because the architecture of Android works in such a way that you're going to have producers in probably a separate process and consumers in another process. The typical example of this is you have your media codec stage fright, which is going to be doing video decode, which is the producer, which is going to be writing into buffers. And then you have Surface Flinger, which is going to be consuming these buffers in its own Surface Flinger process. So to do that, you basically have to solve the general kind of producer-consumer threading problem, where you need to have a synchronized buffer. So that's what buffer queue is. You've probably heard about it before. It's behind a lot of the core rendering stuff on Android. And of course, this has to be synchronized because you don't want to be writing to a buffer as you're grabbing it to show it on the display, because otherwise you might see tearing or partial frames. And SurfaceTexture has this API called update text image. So update text image, what it essentially does is it says, okay, I want to access the buffer right now, the latest one you have. So remember, the video decode is going to be writing into these buffers, and you want to make sure that you get the latest one so you're not grabbing a previous frame, for example. So update text image basically does the synchronization, and we have these GPU synchronization primitives. It's called the GL fence. So basically what it essentially is it says, I'm going to use this buffer, nothing else that's writing to it, don't access this buffer right now, I'm going to use it. and then it'll allow you to actually be able to use it for your rendering. So a use case for this is 360 video rendering, which is something that I worked on. And I gave a talk about this at DroidCon SF a couple of years ago that you can find on YouTube. So basically, when we do 360 video rendering, we're going to use a TextureView as basically a 3D rendering surface. So when you attach a TextureView to the view hierarchy, it generates the surface texture. And in that surface texture, we can create an OpenGLES rendering context, and we can do OpenGLES rendering. So for 360 video rendering, it's a very simple scene. We're just going to be rendering a cube. It could also be a sphere. And then you place the player inside that cube, and then the player can move around, or the camera can move around and look in different places. And then we're going to apply the video texture onto that cube. So that creates this illusion where it seems like you have this seamless 360 experience. So we use the TextureView for OpenGLES 3D rendering. And we need two surface textures. So not just the one that you get when you attach to the view hierarchy, but we're going to allocate our own. And this is actually pretty simple to do. All you do is you create a texture in OpenGLES, and you mark it with an external texture kind of tag. And I'll talk a little bit more about what that actually means. So that's the texture that you're going to pass to the video decoder. Like ExoPlayer is going to handle that, or MediaPlayer is going to handle that. And then the video decoder is going to write into that buffer, and then you're going to use it as a texture on your 3D scene. This is what it looks like. If you guys have never seen 360 videos, I mean, it's pretty easy to find. You can just like search for 360 videos on Facebook, or you probably see it on YouTube or something. So this is an example of what that actually looks like. So it's a video that you capture all around you, so it's not just from one vantage point like this, which means that I can now move around. And basically, you just have some kind of geometry that it's going to be 360 degrees around you, and you're just moving the camera within that geometry. So that's 360 video rendering. And I wrote some sample code for that DroidCon talk that I mentioned. So it's under the FB samples on GitHub. So if you actually want to see how 360 video rendering works, it uses TextureView. It allocates a second surface texture and basically uses MediaPlayer, not ExoPlayer, but that's just for simplicity's sake. So I've been talking about this ExoPlayer thing, and you guys probably all know that ExoPlayer is kind of the way that everyone is interfacing with MediaPlayer or with Media Codec. So what it gives you is like adaptive bitrate streaming and all these different functionalities and different abstractions that you can play around with. But a key thing here is that it gives you flexibility in what the sync for the video decode is going to be. So you can provide a surface holder, a surface view, or a texture view. So it's compatible with like any kind of rendering that you have, which is important. So we talked about Media Codec. So Media Codec is the thing that's actually going to be responsible for decoding the actual video chunks. So it's going to be used in conjunction with Media Extractor. So it's going to extract chunks, and then it's going to decode them, and it's going to write into the buffer queue, or the buffer that comes out of the buffer queue, which is essentially that surface that we talked about. So that looks like this. So in the case of surface view rendering, you're going to have this architecture where you have the surface, which manages this buffer queue, and you have graphics buffers. You can have anywhere from 0 to n. If you guys heard about Project Butter, where the app window is going to be triple buffered, in that case, you would have 3 of these graphic buffers, which are going to be in the buffer queue. So what that allows you to do is you're never, if you can't keep up with rendering, you can still grab the old buffer from the buffer queue. So the Media Codec is going to be the producer, and this is it's going to work asynchronously. Actually, now media decoding can be in its separate process, but the Media Codec in stage fright is actually going to be writing into the buffer queue. So what it's going to do is it's going to call DQ buffer to grab a buffer from the buffer queue, and of course this has to be all synchronized, and it's going to call Q buffer when it's finished writing. So now you have a buffer that's available, and then when Surface Flinger actually goes to do the composite for the display at the VSync rate, which is going to be at 60 frames per second in general, it's going to do acquire buffer to grab the latest buffer and then release when it's done with that. And that's kind of the flow of how all this stuff works. And this is for the surface view case. For texture view, it's a little bit different. So you're going to have your surface texture, which is going to manage the buffer queue. And again, it's going to essentially just have the same graphic buffers behind the scene. And I'm going to mention in the next slide what those are. And Media Codec is still the producer. Whether or not you're using MediaPlayer or ExoPlayer, in the end, your lib stage fright is the thing that's actually going to be writing into the buffers. and then this thing called render thread, which is in your app. So I think this happened after Jelly Bean, I believe, where they made a separate render thread for doing stuff. So what ends up happening is when your app is going to render out the view hierarchy, essentially, it's going to render it into the app window. And while it does that, that's what's going to be consuming the video texture. So the video graphic buffer is going to be latched by the render thread in something called HWUI, so the hardware UI. So this is doing like all like the hardware accelerated rendering of your view hierarchy, your normal view hierarchy. And of course, the video is now going to be included with that when you're using a texture view. So that's going to be consumed during that process of rendering out your actual app window. And then now your app window is going to have the video composited with it. And then that whole app window is going to be passed to SurfaceFlinger. So I mentioned this thing called graphic buffer, and that's essentially the same thing I was talking about before with these external textures. It's also known as the EGL image. If you want to create it in OpenGLES, there's this tag called GL_texture_external_OES. And basically all it is it's a gralocked buffer that resides in GPU accessible memory space. So that's at like the lowest level of what this is. And a gralocked buffer is, if you guys have done C development, it's like malloc, but it's for graphics memory. This is something that the hardware abstraction layer needs to implement. So you could be a chipset vendor like Qualcomm. You would basically provide the implementation for how to allocate memory that is going to be accessible. The key thing is that the memory, it needs to be something that can be shared across processes. So it can't just be in memory space that only your application can access. It's going to be used from different places, and it needs to be synchronized across different processes. So that's all that we're talking about when we're talking about this graphic buffer. It's behind your SurfaceTexture or your TextureView, or sorry, your SurfaceTexture or your Surface. In the end, you're just talking about a 2D array of image data that's going to be held in shared memory space. That's all we're really moving around here. And of course, when you create these gralock buffers, there's different flags that you can set. And if you needed it to be DRM'd, what that would mean is that you're doing a gralock with this flag, gralock usage protected, which just means that nothing else can access that buffer. So that is kind of at the core of what all video processing is. It's just managing these EGL images or these graphic buffers. And that is kind of like the core of how all video rendering is implemented. So I want to spend some time to talk about the differences between rendering with SurfaceView versus TextureView. How many of you are familiar with Graphica? Graphica, anyone? No? Okay, so a few people. So Graphica, Grafika, is a open source project by Google. It's not really an open source project, it's just like sample code. So you can find it on GitHub, and basically it has a bunch of rendering and video use cases. So little test cases like double video decode, rendering with a surface view versus a texture view. And it allows you to kind of test out different scenarios or like camera capture on different devices. So this is like the tool that I'm using for testing surface view versus texture view. So they basically just have playback of a video. You could loop the video and then play it at 60 FPS. So we're going to be kind of digging into what's going on when you're rendering with surface view versus texture view. So we have a few tools that we can use here. One tool is Adb Shell Dumps Surface Flinger. So this is like a system level command that you can call, and it's going to dump out a whole bunch of information. And the relevant part is going to be in this section here. I'm going to zoom in on the parts that are what I want to call out. So what you're going to get here is a list of basically the layers that are going to be composited by Surface Flinger. So in the case of Surface View Playback, you're going to see that there's going to be an explicit Surface View layer. So this is actually the video layer that we were talking about, that video buffer that's going to be composited by Surface Flinger. And then there's also this Android Graphica Play Movie Surface activity, and that's the app window. So we have both the app window and the video surface that are shown in the hardware compositor. So these are the things that are going to be scanned out and then rendered onto the display. And the HWC is just a hardware composition, so it means it's not doing OpenGL-ES composition. It's just going to use a straight up hardware layer. And these devices have a fixed amount of hardware layers that you can actually use to render this. Another thing that you'll see in that dumpsys output is some output. Well, it depends if you have a Snapdragon device, which is a Qualcomm device. You'll see this thing called the Snapdragon Display Manager, I believe it's called. And the key thing that I wanted to call out here is that it can show you the underlying format of the buffer that it's using. So in this case, you can see that it actually breaks up the video buffer into two of these surfaces that are 512 by 640 to create the one video. And it keeps it in the native format. So you can see there it has a format of YCBCR420. So this is a native video format, and it's not in like typical RGBA 88888, which is what we would use if you're doing like GL compositing. This is very important because what that means is that we didn't have that additional conversion step, which means that it's the most efficient way essentially to render the video. We didn't have to convert, we didn't have to use additional memory, we didn't have to use additional power to actually display the video pixels. When you use a texture view, it looks like this. So in this case, you'll see that before there was 6 layers, and now there's only 5 layers. And of course, you just have the app window, and there's no additional layer. Why? Because the composition step of the video was already at the render thread level. So the app's render thread is the thing that actually composited the video. So now there's only one window that you send to SurfaceFlinger, which is good. And then the rest is just like system UI that's being composited in SurfaceFlinger. And then again, if we look at the Snapdragon Display Manager output, you'll see that we don't have that additional third layer where it has the video in its native format. We actually just have the app window. So which means that you did pay that conversion where you actually did that additional, effectively an additional copy of the video into the app window. Another way that you can look at this is with a tool called Systrace, which many of you are probably familiar with. It's a great way for looking at the internal details of the system. If you call Systrace with GFX and View and Sched, that'll give you the data that you need to observe what's going on in the buffer queue in these two examples. So when we're playing back with a SurfaceView, you'll actually be able to see if you look down at the SurfaceFlinger process section that there's a section called SurfaceView. And in that section, you can actually see as the buffer queue is being exhausted. So I'll show you in a little video. So there you can actually see the ticks of, that's basically the buffer queue being consumed. So as it like goes up and goes down. And in this case, there's only 2 buffers, and you can see the value down there. So as over time, as the video continues to play back, you're going to see the value go between 0 and 1. And if you're doing like 60 FPS video playback or something that might not keep up, you might need to use an additional buffer. And this is something the system would handle. So in this case, you just have those 2 buffers, and you can see as the buffer queue is being exhausted right there in Systrace. In the case of TextureView, you can actually see a little bit more because there's that additional render thread composition step. So you'll see the section for the render thread, you see the frame that's happening, and you see the row for SurfaceTexture. So in that SurfaceTexture row, you're going to be able to track the buffer queue of the SurfaceTexture. But then remember, there's also going to be a buffer queue for the app window itself. And in this case, because we're going to be playing back 60 FPS video in the example, what you're going to see is there's going to be 2 buffers, not 1, in the buffer queue for the app window. So in this case, I'm going to just toggle between the SurfaceTexture buffer queue, and it just goes between 0 and 1, like I said. And then you can see this render thread section that I'm going to zoom in on. And there you can actually see where it's calling the acquire buffer and the release buffer, which is the thing that is going to get the graphic buffers that you can write into or read from. And then now I'm going to scroll and find the section that has, yeah, there it is. So now you can see that the app window section. And if you look at the value down there, you're going to see it's going to be toggling between 1 and 2. Now, I mentioned the Project Butter stuff. So like for Project Butter, there's cases, like for example, actually probably if you're scrolling through a feed where it might be triple buffered just to make sure you don't have that additional latency. So in this case, it's just going to be double buffered for the app window. So that's in Systrace. If you actually, so I mean, in Facebook, we're pretty serious about like performance. So a lot of times we end up going deeper than the framework, Java layer, and deeper sometimes than the layer under that. And in this case, I actually made an Android open source project build on my Pixel 3, so I can actually debug into like the code to see what's going on at the in actual C++ code. And most of the rendering in video code, it's all like the Java code is just a thin JNI wrapper on top of actual real C++ system level code. So in this case, we can kind of track what's going on with queue buffer, dequeue buffer, acquire buffer, and release buffer, and see which are the players on the C++ side that are actually handling this stuff at the system level. So in this case, I just did a debugger call stack of what's going on when queue buffer is called as we render with SurfaceView. So in this case, you can see that you have the Android Surface queue buffer being called, and then you have this thing called a codec, which lives within libstagefright, which I talked about. A codec is kind of the thing that's happening behind the scenes with MediaCodec, which is the high-level Java thing. And a codec stands, I believe, for asynchronous codec because it's processing these chunks of the video decode asynchronously. And I believe there's another path where you may be doing it synchronously as well, but it just depends on where you're going. But here you can see that it calls on output buffer drained, and then it's going to be queuing the buffer. Actually, I should have showed dequeue buffer first, but it's a very similar thing. So you're going to dequeue the buffer from the buffer queue. You're going to grab it. The A codec is going to be writing into it with the hardware codec, which is implemented by like the chipset manufacturer, like Qualcomm, and that's what's actually going to be decoding your buffer and then providing that video. And then it's going to queue the buffer when it's ready to be consumed again. Now, when you're rendering with SurfaceView, you're going to be calling acquire buffer from the Surface Flinger process. So if you're actually debugging this and you were like attached to your app process, essentially like the Graphica process, you would see that you're not going to see any acquire buffer calls. The reason for that being it's actually Surface Flinger itself, the process, that is going to be acquiring the buffer, and there's no acquire buffer that's going to happen in your app process. So in this case, we see this thing called buffer layer consumer .cpp, which lives resident in the Surface Flinger library, and then there's this other thing called buffer layer, which actually calls latch buffer. And latching the buffer just essentially means grab the latest frame. That's going to be synchronized with these GL fence syncs, these synchronization primitives, so that you can access the buffer in a safe way. And then similarly, after Surface Flinger has accessed that buffer and then written it out to the display, it can then release that buffer and then provide it back to the buffer queue so that media codec can then write into that buffer again. So that's what that looks like. Again, this is all going to happen in the same code in buffer layer consumer and buffer layer .cpp. So if you did have serious performance issues and you wanted to like really figure out the details of what's going on there, you could actually just have your Android open source project build. It's not that hard to do. You can root your it's very easy to root a Pixel device, and building the Android open source project is not that bad, especially if you're doing it on a Linux distribution. So in the case of TextureView, it's going to be different. So the acquire buffer call is going to happen in your app process, and it's going to happen on the render thread. So you can see here that we have this thing called buffer queue consumer, and it's going to be a delegate of GL consumer. But the more important part is this deferred layer updater, which is calling update text image. So you can see that's in the HWUI library, which is the library that's responsible for rendering your whole view hierarchy. This is something that so now like a lot of your view hierarchy rendering is hardware accelerated. So when you draw fonts or when you draw lines or colors, that's all going to be rendered by the GPU now. It didn't used to be back in the day. It used to be software rendered, but all that stuff is now hardware rendered most of the time. So along with that, it's going to grab that video surface texture that we talked about, and it's going to render that into your app window. So that's why we see the acquire buffer happening on the render thread in the app process. And then similarly, when it's finished with that, it's just going to provide release the buffer back into the buffer queue. So now when we're thinking about optimizing for video feed scrolling performance, we kind of have to think about all this stuff that's going on behind the scenes. So we talked about the fact that if you render with a TextureView, it's going to be more expensive because of the bandwidth and the conversion and the additional power costs. But now imagine that you put all these, it's not just one video, but you have multiple videos scrolling through a feed, and it could be fairly infinite in the sense that I can keep scrolling through my Instagram video feed and still find stuff. So what we're worried about here is TextureView churn, because if you use a recycler view, you're going to know that every time you put the view off screen, it's basically going to detach to the texture view. What that means is that it's going to detach the surface texture, and then that's going to destroy all the underlying graphics buffers that we talked about. And this could be expensive. So we want to prevent that surface view and texture view churn during scrolling, and we know that the video surface is going to be created on view attached to window if you're using a recycler view, and we know that the video surface is going to be destroyed on view detached from the window. So everything in that buffer queue is going to be wiped out, which we don't necessarily want to do. And so what happens when you actually create this surface texture or the surface is you know that you're going to do these allocations of the buffer queue and graphic buffers. And we know in general when you're doing animation that you don't want to have to do these, you don't want to do Java level allocations because there's going to be garbage collection. These are native allocations, so we don't have to worry about that as much. But it could be a performance hit on some older devices to actually have to do that allocation. But generally, this should be super fast to allocate these. This is actually not your bottleneck. What your bottleneck, or what the big thing that could cause frame drops can be, is the media codec initialization, which has to go to the hardware, and the video decoder initialization. These are the two key things that you want to avoid while you're scrolling through your feed. So in the destruction, you're going to release those buffers. This is just a surface or Systrace output of what's going on. And you have to shut down the video decoder, which also can be slow and expensive. There's an orientation change that can also have the same problems as scrolling through a video feed, because when you do the orientation change, it's also going to disconnect or it's going to remove the texture view from the view hierarchy, and it's going to reinflate things. So if you want to have a smooth transition from inline to full screen, you have to worry about that. So yeah, the video surface will also be destroyed, so you need to avoid the video decoder teardown and recreation. And you need to find a way to basically keep the decoder's output surface around. And I'll talk about a few ways to do that. This is an example of how iOS devices handle this. So that orientation change transition. And you can see they have like this smooth animation, and then you can basically just switch from portrait to landscape very seamlessly. This is what it looks like on Android right now. And this has been the case for like 8 years. And this is even if you're keeping the output surface around. There's actually, I don't know if you guys can see it, but I can see it because I'm a graphics engineer and it really bothers me. So this is what it looks like if I capture that freeze frame. So you can see that there's a bunch of like stale frames essentially that are rendered to the display that haven't been cleaned up essentially as you're doing that orientation change. So it's not a smooth transition. This is just a bug with Android, essentially, that needs polish. I mean, part of it is because of the fact that it's going to reinflate the whole view hierarchy and change the way it's rendering. But this is something that definitely needs polish. So to improve video feed performance, I could do a whole talk about this, but we only have 40 minutes, so I have to finish up soon. Obviously, you want to do network prefetch to make sure you have the data. You want to do codec warm-up. So you can actually pool or cache your media codecs. So you can allocate them up front. You're going to know what you're going to use if you are responsible for your own video. And you can find a different way to keep the media surface around during recycling. So one way to do that is keep the texture view attached to the recycler view. And there's ways to do that. You can override the recycler view, or you can find some way to keep it attached to a different part of the view hierarchy. Another approach is to just keep the surface texture around. It's not actually the texture view that you have to worry about, it's the surface texture. So you could override texture view and then make sure that it keeps the surface texture across orientation change or when you're scrolling off the view in a recycler view. A potential thing that could be of help here is to just pool surface textures. So I mentioned that for 360 video, we create our own surface texture. So you can basically just create a pool of surface textures and then have your texture view just grab from that pool when it needs to. And this would avoid the extra allocations of those graphic buffers and buffer queues. And one thing that I've been thinking about that I actually haven't verified that it would work is you could essentially just have like a video player server. And what would happen is as you're scrolling, you would always have this video player active, and it's the only video player active because you know that you're only going to be playing one video at a time. And what it would do is that it would be always warmed up, and the video decoder would never deinitialize, and then you could just write to whatever is the current video frame that you need to be showing when you're actually autoplaying video, and then otherwise just use the pause frame or your poster frame as you're scrolling through the feed. So this is an idea that I thought about. The important thing is to make sure it's power efficient, that you can actually run the video decoder without it actually consuming power, which I believe should be possible, especially if you're just like outputting black frames or something. So that's an idea I had, but I haven't actually tried it. In the worst case, you could scroll at 30 FPS. So for those that know about animation and rendering, it's much preferable to have a solid 30 FPS rendering than to try to render at 60 FPS and have it be jittery. The user sees that a lot more than if you just fixed your animation at 30 FPS and then consistently always made that. So this is kind of like a last-ditch effort. I don't want you to do this, but you may have to do this on certain older devices, and I think we do this at Facebook on some older devices, where we fix the scrolling at 30 FPS and we make sure that we always hit that. So that is my talk. There's a lot more I could go into, but I want to leave time for questions. So anyone have questions? Yes?
So in the end, you mentioned TextureView.
Yes.
Why didn't you go with the SurfaceView? As you said, there's no color conversion, and it sounds like it would be more efficient.
Yeah, so I was just going through the example of just showing what's happening. Yes, you should use SurfaceTexture. I mean, you should use SurfaceView when you can. In the case of 360 video rendering, we can't, because of the fact that we need to do the 3D rendering. So there's certain cases where we can't actually use SurfaceView. But if you're just doing video rendering and that's it, you don't need to do any 3D stuff, then yeah, it is better now after Nougat to use SurfaceView because you don't pay that additional cost. But like in the system, this stuff is happening no matter what if you use a SurfaceView or a TextureView. When you scroll, you're still going to be allocating these additional things. You're still going to have to do the video decoder init and the codec init. Yeah, it's not predominant, but there's also the higher level kind of recycling of the texture view as well. So we want to share the texture view between regular video and 360 videos as well. And then we also have not just video, but we have like 3D posts, like 3D photos and stuff in the feed. So that's another thing we have to worry about. So sometimes we'd rather share the texture view. But like if you're doing full screen video, it'd be better to just use a Surface View. And if you only have video in your feed, then yeah, it'd be Surface View after Nougat for sure. Am I done? Out of time? Or have one more? Anyone? Questions? No? Right there. Right.
I have naive questions. What about Vulkan?
Yeah, so Vulkan, you can render into the texture view the same way as you did with OpenGLES with Vulkan. So Vulkan is just another graphics API that allows you to access the hardware, GPU acceleration stuff. Vulkan saves on CPU cost. So it doesn't help you with GPU. So if you have like a ton of polygons that you're rendering or something like that, Vulkan doesn't help you. But what it does help is with the overhead of the driver. So that's what Vulkan is trying to solve, is that additional overhead every time you made a draw call with OpenGLES, you'd be paying this additional cost. And Vulkan takes that away so you can do more draw calls and have less CPU cost. And actually the HWUI stuff that I was talking about, that's going to move to Vulkan at some point. So your Android system rendering is all going to be in Vulkan, maybe in the next release of Android. So Vulkan is the way forward. Cool. All right, thank you.